I'd like to know what is the equivalent delta V that you're getting in Jupiter in here? You know,
So in order to do the UPS transit as showed requires a C3 or a V infinity leaving Earth of just over 9 kilometers per second. And to do a straight shot to Uranus requires about 11.6 kilometers per second. So you save that difference of roughly 2.5 kilometers per second.
but that's not what I want to know. I want to know what is the delta V that you're getting at Jupiter. In other words, if you did that without, if Jupiter wasn't there, what delta V would you have to apply to get the same distance?
If we waited until we got to that point in space to apply the delta V?
Just assume, just as a simple trajectory calculation, if Jupiter was not there, what delta V would have to be applied to get the same effect?
I'm not sure.
I don't want
have
you to
that
ask me
offhand,
standing
but-
up.
Yeah. Okay. Okay. And also to
Well, Jupiter's
correct-
giving you a delta V, that's where you're going.
Yes. Yeah.
And I'm just asking, well, what would be the chemical, the equivalent, same thing? What-
Well, it's
what
equivalent to
rocket
2.5 kilometers per second at Earth.
And like Nathan's saying, if Jupiter wasn't there, you would have to provide the additional 2.5 delta V to reach Uranus with a straight shot from Earth.
I'm not asking you, yeah.
We'll have to run some numbers to get that number due. We don't have that offhand right now.
All right, well, thank you, Alakai. My name is Joshua Shoyck, and I'll be presenting our probe vehicle. I'll be going over our requirements, as well as our vehicle description, budgets, some CONOPS, and specifics about our entry and separation. Next slide. So our external requirement from the RFP was that we had to measure the Uranus atmosphere phenomenon. And so some internal requirements that we developed was that we had to be able to survive entry, which was important. We have to forward this data to our carrier vehicle. We have to be able to operate autonomously because the moment that we separate from the carrier vehicle, we have no receive capability on the probe to update it anymore. And so it's very important that we have to be able to also send updates to the probe during transit when we do have the ability to do that. And we have to be able to recover from any single event failures during our mission. Next slide. So, starting off with transit, from the moment we leave the Earth, we will be attached to the carrier vehicle and we'll be mostly dormant throughout most of the transit. Each probe, though, will be cycled through a system check, a 9-month cycle for each probe, in which one probe is updated at a time over a period of 3 months. And so this will allow data to be relayed back to Earth and troubleshooted and then sent back to the probe with a system update. And so the plot over here shows what that system update patch would look like. And then during our transit also our batteries are kept charged because we're using secondary batteries. And so that's to make sure that they're at the proper optimal power for when we release. And the last system check happens 10 days before we release from the vehicle. Next slide. So our CONOPS for our release, we are released roughly 70 days before we enter the actual atmosphere. And our release time, we are released with an initial actual velocity of 0.3 meters per second. Now this speed is just chosen to give us a small ability to separate from the vehicle before it does its maneuver to get off of the impact trajectory that it was on for releasing the probe.
Is that a spring or something?
Yeah, so that's going to be released with springs. And so both probe systems are delivered with a little bit of spin on them. The probe doesn't necessarily need to have spin upon release, so that's why on the orbiter it has just a very small half RPM rate. This is just to help ensure that we definitely do not come in backwards or we are below, or we at our proper angle of attack for entry. With the UPS, however, since it is spin stabilized for most of its transit, we decided to use that for our advantage and have a 5 RPM spin rate for the probe and releases. The spin on the for the orbiter probe is accomplished through our release mechanism. So about 5 minutes after we release then, our system's powered down for our transits. We have a long transit phase. At this time only a timer is on, which returns back on before entry. Next. So this animation here shows the orbiter paths of the probe and the carrier vehicle. And shows our sensitivity analysis we did for that. So what we did is we basically ran Monte Carlo simulations to figure out where our errors could be. And so errors come from GNC inaccuracy, ephemeris inaccuracies, as well as probe pointing error due to the release. So what we have right here is you have the, that's the probe trajectory, the impact point, and that's the paired vehicle. These series of dots right there represents when we have comms link at the moment of entry. And these dots right here represent when comms link ends, when probe batteries are failed. Next slide, please. So this data right here just shows basically the results of our simulations. And basically from here we can see that we reached within our parameters for our entry. Our alpha is below 5 degrees, as well as our gamma for entry, which is our flight path angle, is -40, but it's within our range that we can accept. The delta V required for the carrier split is kept at 23 kilometers a second. And then our probe time of flight is 70 days across all these. Next slide, please. So for our probe pre-entry ghost phases, again, we are under a timer for most of the time in dormant. Within 17 minutes before entry, the timer will turn on our probe systems. We'll begin calibrating our instruments, and the accelerometers on this will start collecting data. After that, we have a wear time of roughly 12 minutes, there plus or minus 4 minutes before we actually begin entry of the atmosphere. And entry is defined as the moment we start experiencing 15 micro Gs. Next slide, please. So basically our descent profile, shown over here, starts off with our entry, in which we experience our peak heating and the acceleration phases. And this will last for roughly 53 seconds. After that, we slow down to a speed of Mach 1.2, which we can safely deploy our drogue parachute. And we begin our deployment ejection phases, in which we separate our heat shields and deploy our main parachute. Main parachute comes out at 2 minutes into our mission. And at that point, we then begin collecting our science data. So our minimum amount of mission time we could have for descent is 60 minutes. But our batteries have been sized for a time of 100 minutes with a possible 2-cell battery failure. We expect to be reaching 5R around 85 minutes after entry.
How much of the atmosphere will you penetrate?
Is Jason here?
Jason here, but I can answer that question. The planet, we believe, is an icy core, and then above that is an ocean of liquids and such. And that's at super high pressure. So the most part of the planet is actually a gas. We will just be scratching the surface. We could easily drop down to 300 bar and still be in a gaseous form of the atmosphere. So we'll only be scratching the very tip top from 1 to 5 times Earth's pressure.
What is the altitude change, I think is the question.
That altitude change of the will be
somewhere on the order of 100 kilometers.
How much?
100 kilometers.
All right. Next slide, please. So this just shows our mass budget for our system. Same as the other vehicles presented. We have our estimated mass with our margins applied, and our design mass, and then finally our allocated mass. So our design mass is below our allocated mass. So we're sitting at 137 kilograms. Next slide, please. And then this just shows what our operating power is. This is power for when all instruments and components are turned on during our descent, which is our largest power draw. So we'll be using 80 watts power, which our batteries are sized for. Next slide, please. And this just shows our communications link. This is why we go into more detail later with the communication subsystem. But for now, right now, our effective data rate is 80 bits per second, and at our 1 bar altitude pressure depth, we have a margin of 12 dB, and at 5 bar, we have a margin of 6 dB. Next slide, please. And so then this is our data budget, showing our total MIPS usage. And so the total usage is below our available usage provided by our system. Next slide, please. And so now I'm going to go over a little bit of the instruments we are carrying. Our first instrument is our atmospheric structure instrument. This is a heritage instrument from the Galileo probe mission. It has accelerometers, as well as a pressure sensor and temperature sensor. For this, it will be accomplishing the part of the RFP that requires us to measure the structure of the atmosphere at the descent point and its data rate. During our entry phase, the accelerometers will be collecting data since they require no access to the outside environment. And then we'll be storing that data and then transmitting it back at a later time when the heat shields are removed and we have the comms link. So that's why we have the 25.5 bits per second data rate collection during entry. And then once we begin our nominal science phase, our total bit rate will be 18 bits per second. Next slide, please. For measuring the noble gas balances and isotopic ratios of helium, hydrogen, oxygen, carbon, and nitrogen, we will be carrying a mass spectrometer, the UNS Pro mass spectrometer, which is, again, also a heritage mission from the Galileo mission. And this has a science rate of 32 bits per second. And we're measuring from 150 millibar, is capable of measuring from 150 millibar to 20 millibar. Next slide, please. And then finally, we have our nephelometer, which will be used for measuring the cloud particulate structure as we descend. This is heritage mission from Pioneer Venus missions. And it has a data rate of 16 bits per second. Next slide, please.
The reason for using something that has heritage from Pioneer Venus is nobody's built anything better since then.
That's actually true. We have not found what it is because our probes, we have to carry 3 probes, and we're so concerned about mass, we have to keep it as light as possible. So one of the big factors in choosing a lot of these instruments is in the mass of these instruments. The Pioneer Venus nephelometer, so we have found has so far been the smallest mass and power consumption of any of those.
But you probably are using new chips.
Yeah, there will be an upgrade. This beyond the scope of our capabilities to be able to update these instruments to figure out what a proper mass is. So we just have to basically fly with the heritage as they presented.
These are all CFE provided equipment, right?
Yeah. Yes, customer provides all these instruments too.
Guys, that's comment, that's getting what? Because the guys that designed that instrument now they retired, and they're probably long past.
Obsolescence.
It's a customer's property.
Well, we're trusting the customer to be able to
There you
deliver.
go.
We really want this.
Alright, that's even better. That's even better. Right.
All right, next slide, please. So now we're going to go a little bit into our vehicle design. We started off by looking at our pressure descent module, which for our design we used a pressure vessel similar to what Pioneer Venus used. This was used to basically protect the components inside of the probe. And so our initial low pressure, our internal pressure for our system will be 14 psi, and then inside,
Why is it pressurized?
pressurized to basically protect the components inside from the atmosphere, from the 5-bar depth we go to.
So are we never gonna go fully metric?
I would like to keep it metric, but I put the inches on there just for people who don't know metric so well. I'm hoping the converge is here. So our diameter is 60 centimeters, and our so 25. And our height 55 centimeters. And so that this module contains our all instruments, comms, computer data handling, power systems, as well as parachutes. Next slide. And then protecting that descent module, we have our front and rear heat shields, providing our thermal protection. For our design, we have a 60-degree half-angle heat shield. And our total diameter is 1.17 meters. Next slide. So now to talk about some of the internal components of the descent module and the layout. Basically, all our components are mounted onto a equipment shelf that's being made out of aluminum beryllium alloy. Of note, we have the mass spectrometer, which has to be mounted through the equipment itself due to it being the longest component we carry. This is not usual though because mass spectrometers on both the Galileo probe and Voyager probe mounted in similar way. And then we have our comm system mounted on top outside of the pressure vessel with our parachute. And then our top and bottom nodes are made out of titanium alloy. And they have ports for access for the instruments. The gas inlet for the mass spectrometer on the bottom, viewing windows for the nephelometers, and then ports for the
Is there any special, it sounds like you've got mounting holes that are tapped directly into the albumet.
Yes.
So when you bolt something into it, is there any special care you've got to take going directly into the albumet material?
Not that I am aware of, but I understand that special precautions must be taking place, that the instruments must make sure that they are aligned and carefully placed within the region.
I'm not concerned about alignment. I'm concerned about the fact that albumet is hazardous. And when they machine it, there are a lot of special things they need to do. And I'm concerned that if you bolt in and do something to damage the threads, you're going to have this toxic material floating around.
We know that we should take care of the necessary GSC and trained personnel in order to handle this equipment shelf. So that is also taken into account.
I'm not talking about GSC. It's hazardous material. So, I mean, if you screw in a cross thread or something accidentally and start to damage that material, you've got poisonous material floating around. So,
At this time, I'm not prepared to answer that
Okay.
question concerning the safety
Okay.
of the.
I think you want to say the word insert.
what?
It's
Yeah.
not insert, is what you want to say. Because you replace it insert.
So then we also have support for allowing our harnessing that comes from the carrier vehicle for supplying our power and checking our systems. And then we have our separation brackets mounted on the outside of the probe, which attaches to the front rear heat shields. Next slide, please. So here we have top and bottom view showing the components where they're laid out in the vehicle. And so we have two redundant computers. We have two computers, one for redundancy. We have our comm system mounted on top of one of our computers. We have our ASI electronics and UPMS with our accelerometers mounted in the center of the probe. And on the outside, we have our separation nuts on top of our brackets. And then here you can see the bottom of the UPMS with the gas inlet, our nephelometer looking through the view ports, and then our 9-cell 2-string batteries packs with our PCB and spread throughout the thermal control our HUs. Next slide, please. So attachment of the probe to the carrier vehicle, we attach at 3 points for the orbiter spacecraft. We basically use a monopod, tripod, bipod system. And the probe is located on the side panel of the orbiter spacecraft. And so our separation mechanisms are set up to give us both a axial velocity and a rotational velocity. And so that's why they're angled at 88 degrees from the separation plane.
What type of pyro devices are you using?
We're using separation nuts for the pyros. This is because the redundant systems on the pyros fire at the same time as the main. So if the main charge fails, the pyro releases at the exact same time, so we'll get an even release with all systems.
Does any of your sensors have a pyro shock sensitivity?
All our sensors have all flown on other probe missions, so we haven't been able to find any data about that.
Yeah, something you just might want to be aware of is certain test instruments are susceptible to pyro shock going through your structures. So sometimes you might have to isolate them. Even though they've flown, your pyro positions might be different than heritage. So you just be aware of inducing pyro shock into your test instrument.
I will look into that. Thank you.
So it looks like you're holding it and you're releasing, and your release mechanism kicks it off at an angle and it parts to spin.
Yeah.
So that means all those things have to be fired at almost the exact same time.
They do.
Right.
So any error in the release of those could lead to error in trajectory.
Well, it also leads to error in the wobble, and,
Yes.
so the pointing, so is all of that taken into account with these fine numbers that we've seen before? Four-place decimals?
Yes.
Josh, I'm curious, stuff that, because I haven't in your allocations of the budget and your outlines here, you've been showing pyros kind of on par with the subsystem. I mean, when I look at those subsystems, I think they're arranged in that order because I can go to SMAD, I can go to other references, and I can kind of see, do we have kind of the right allocations of mass or power, but pyros stick out to me as, is that on par with the subsystem? And somebody probably early on in their program said, you know, pyro, we got a lot of pyros, so maybe we got to set those aside as a separate line item in the budgets and that. Was that done intentionally by you guys, or maybe Highshare, somebody's a sponsor for your program and you want to highlight that? I don't know.
Yes, it was decided that we needed to have a pyro subsystem
Because there's so many of them.
recently, yes, because there's so many of them, and it was something that we actually had not looked into in detail, and we realized we need to have a team dedicated to looking into it.
Just dedicated to that, okay. That's great.
All right, next slide, please. So now for the UPS attachment, it's similar in the sense we have 3 connection points, but this time we only have 3 bipods for our attachment fitting. And because the UPS is spinning, our separation does not need to spin us up, so it's just giving us an axial velocity. So it's a little bit simpler in its release. Next slide, please. And so now for the, also for separation, we are held in with bolts attached to separation nuts. And so this allows us for an even release for when they're initiated. Springs then push the probe away from the carrier vehicle. Springs of the size are fairly similar across all vehicles, except for the differences in tightening, torquing of the springs, retensioning. And then for our harnessing, for releasing of that, basically we kind of use a pull-out method in which the harness is lined up with the axis of our separation. And so when the probe separates, it's allowed to simply just pull out, and there's no need for cable cutters to cut those cables.
That can't become a shakeout mechanism?
Hmm?
It can't also become a shakeout mechanism? Pull out?
I was actually not aware of a shakeout.
I'm just saying, I mean, if you have something that will pull, just pull out, well, what's the risk that some other vibration is going to cause us to disconnect? It's long before.
We haven't designed the system fully, so I don't know whether it would be something that have to be designed to make sure that there would be no way that the system could fall off by accident during the transit. And we could also look into some type of mechanism to shake it loose or prevent it from shaking off.
What about the disconnect on the orbiter, since you're spinning off of the orbiter?
So that would have to be angled properly for the way that it's spinning. So this is the actual picture of the orbiter itself showing it. For the UPS, it will be just simply, since we're leaving axial from the UPS, but the one for the orbiter will have to be angled properly for that release.
So you are separating at an angle from the spin axis of the carrier, the orbiter, and the tabletop. Is that right? The orbiter is spinning, always.
No, the orbiter is not spinning. The orbiter is 3-axis stabilized.
Oh.
The UPS is spinning,
Got it.
and we're mounted along the spin axis of
Are you,
the UPS.
the orbiter does use spin stable spinning at times, so.
No, it does not.
Never.
No, 3-axis all the way.
Oh, okay, great.
Next slide, please. So then, for the separation of our heat shields on entry, we have the brackets that were mounted on the set module, and those allow bolts to be mounted through that connect to the front of our heat shields. Those are also released by separation nuts, and those pyros are initiated by the pyro card inside of the probe. So in our entry, in our deployment phase, the rear heat shield will come off first to allow access for the main parachute, and then the front heat shield comes off after main is deployed. Next slide, please.
Actually, I have another question. I'm not real familiar with probe entry systems, but there's not an inherent risk of injecting the front heat shield in for whatever dynamic. You're in some kind of atmosphere now, right?
Yes.
Is there some kind of aerodynamic situation where that heat shield could actually get brought back up into the chute and cut your chute lines or things like that, damage your main parachute?
Okay, so I'll talk a little bit more about, there's some diagrams showing the actual parachute ejection phase later on, but the heat shield is attached to the drogue parachute, and then the line is then attached to the main parachute, so when the drogue blows, it releases, and when the rear heat shield separation is fired, it separates and pulls up the main, and then that cable is designed to break off so that the probe is only under main parachute.
I'm talking about your front heat shield though.
Oh, sorry, Mr. G. So fears of the front heat shield breaking off.
Yeah, so say like there's a like the gentleman in front said earlier, you gotta make sure your 3 pyros blow simultaneously. If there's a condition where one hangs up and fires slight delay after, that's gonna hang up your release. Your heat shield might flip in a non-manner that you're anticipating, and it flips back up.
The guy who did all our parachute and trajectory for entry is not currently here, but I believe what would happen is, since the probe is under a main parachute at that time, the way that the front heat shield actually separates is because there's a difference in ballistic coefficients between the probe and the heat shield, which allows it to separate. There's also, for safety, for that actually best reason, springs mounted, smaller springs, just to give it a just in case some sort of failure.
Okay.
Next slide, please. So there would be a velocity profile shown right there, but I don't think it's showing up right now. Basically showing our Mach and speed as we enter. But over here you can see where our peak acceleration and heating forces are during entry. So again, our entry phase lasts for 53 seconds. We experience a max heating of 1,650 watts per centimeter squared. And our max G load is 164 Gs. And then our drogue deploys once the probe slows down to Mach 1.2. Next slide, please.
What is the entry speed? What is the speed at entry?
26 kilometers a second. 22, sorry. So now for our thermal protection system design, with our front heat shield. We basically have 4 layers to our heat shield. We have an aluminum backing plate, this is where the separation units are mounted onto. And then this drives loads through the carbon phenolic honeycomb support structure, which is our main load-bearing layer. This has a CFRP face sheets with an aluminum honeycomb core. And then for our actual heat shield material, we're using an ablative heater, Pica material, which is a phenolic impregnated carbon ablator. And then, so that we did basically going through we ran our entry analysis, and then we sized our ablative off of that. And so the amount of material we have to ablate is 43.9 millimeters, and our total mass is 60.5 kilograms of ablative material. So from that, we size what the ablative material size needs to be for extra margin. And then covering the outside of that ablative layer is an MLI for thermal protection during our orbit phases.
Have you got any degradation in that during the whole trip?
The MLI?
Yeah, we have experience.
Yes, we have. Okay, so now for our actual parachute system, starting off with our drogue parachute. We size our probe, we basically blow a mortar at our speed of 1.2 Mach. Our lid for the drogue is attached with a pin puller and a tension hinge. And so when that blows, the mortar blows, our drogue is deployed. We have a 1.16 meter drogue parachute. And then to basically size those parachutes, we did Monte Carlo simulations to get us within the range of what value we want to slow our probe down. And so we chose our max value there. And our total parachute mass for the drogue is 4 kilograms with our mortar deployment system being 1 kilogram. Next slide, please. And then so for our main parachute, the diagram here, you can see how the deployment system works, but basically we come under drogue at 1.2 Mach. And then our rear heat shield is then allowed to separate, and that pulls out our main parachute. Then once the main is fully deployed, the line between the rear heat shield and the main is broken just by the tension. And then the probe is then under this main chute, and then we release the front heat shield. So our main chute is sized to be 4 meters in diameter. And then we also ran Monte Carlo simulations for this as well to size our descent rate to get us our minimum value of 60 minutes for descent for our sheets.
What happens if the drogue doesn't separate?
If the drogue doesn't separate? At that point, then the system begins falling much faster. The rear heat shield then, sorry, let me think about it. Risk and reliability.
What was the question, please?
What happens if the drogue parachute?
Yeah, if the drogue doesn't separate, something happens with the separation line.
Oh, sorry, so if the drogue doesn't separate, but the rear heat shield separates, then it just means that we're going to have a slower descent rate through our atmosphere.
Okay, but it's still be a safe descent.
Yeah, so it would be safe descent. There shouldn't be any issues with it besides, it would just be hanging around the main parachute. The lines will be sized to prevent any cane.
Well, you know for sure that the spacecraft is not going to it'll descend faster than you're going to choose.
Yes.
That's a part of the question.
Like I said, I don't have a specific answer to that question right now. But then, if you want to talk to Jason, who designed it, he might have a better answer. Okay, so without much, any more questions?
Yeah, I had a question. You mentioned earlier on you had single event recovery requirements. How has that reflected in your calculations, whether during the transit, but really during the descent?
I'll pass that question off to Alex Westfall.
I heard the first part of your question, but I missed the second part. Could you repeat that, please?
I was going to say, there was early on, there was a single event, single event upset requirement.
Yes.
In the, you mentioned, I didn't see anything about it, but how has that been taken into account? I guess potentially your software to recover from it, because everything's going to be real sensitive to firing pyros and the rest of it.
We have 2 command and control systems on our probe, so we are able to recover from that. In case one of our command systems fails, we can move
I can't hear you really. Speak louder.
Okay, sure.
Come closer.
Sorry about that.
We don't get your hearing goes down.
We have a redundant command system on our probe. In the event of one of our command modules failing, we can switch over to a secondary one, which allows us to control the firing from 2 different systems. And I'm not entirely sure which part you'd like me to focus on. Could you please repeat the question?
So, with a single event upset, your computer may not be working, but in all the deployments and that activity with pyros and especially the parachutes, you're going to be getting demands for stuff to happen. And if you do have a delay there, if you have to recover, what's going to, you have the correct recovery time, basically. Is it another computer you're going to have them, it's going to be active redundant, if you will, and the software's going to sense that?
We haven't done an analysis on what kind of windows of opportunity we have to give the secondary commands to fire things again. But our system is very robust, so we believe that we would be able to handle that kind of situation. And we would be able to develop software to have our systems fire everything a second time, even if they fired correctly the first time. It wouldn't do anything, but it would certainly be a redundant backup.
So how does, in the case where you had a single event upset, how does the command system switch over to the other system?
Let me add to that.
Go ahead.
I'm on the command data. Like, they're both on during descent, and they're both tied together with their own data bus, so they can talk to each other. And if one just dies, the other one should just take over from there.
Okay, but you haven't gone into software, you're making an assumption.
No, we have no real software.
One's like a watch, there's going to be some sort of, the other one's watching the other's is on in its performance.
Yeah.
But that time differential, that's what, since you're at this level here, whatever that time delay is, I would want to take into account for all your comps, your firing. Okay.
I would assume that the criteria for the single point failure is...
single effects, they got single point failures.
Yeah, like the parachute, that doesn't go, things again, I assume it still works, but it's a shorter mission.
That's how we work for that. So, for instance, if our main parachute ripped during our entry, We can still collect data, it's just we're going to be collecting it in a much shorter time, so we're going to send back less data. And then another example of a single event failure, like discussed earlier, one of the separation bolts nuts on the heat shield, front heat shield isn't released properly. Springs around that will cause the heat shield to separate later if the pyro ends up.
Well, you know, they do, these are two different things. He's talking about a pit flow.
Yeah, I'm talking about different single and
Oh.
upset. You know, you got your electronics, and some have your programs online anymore. The other computers that have some sort of me okay, type thing, my program to say, hey, he's not working, I'm taking over, and then whatever that delay is, it's just, since the firing area is so sensitive,
Yes.
you should have that account.
Thank you. So without further questions, I'd like to pass it off to
I do have one other matter. What is the time, ballistic time after separation for entry for these things?
After separation from the vehicle,
Yeah, from the carrier to the entry,
70 days.
70 days. And so have you taken into account any magnetic disturbances or whatever on the vehicle after?
I would like to pass it off to Orbit team to talk about the disturbances during orbit.
So as was shown a little earlier, we had the sensitivities analysis of the probe on entry. We took into account, there was a list that we showed there, we took into account the variations of release mechanisms and the orbit itself. We did not take into account variations in the magnetic field because we don't fully understand the structure of the magnetic field.
But you can make sure that you're magnetically balanced.
Yes, okay,
And you haven't yet.
that's correct. We have not looked at magnetic balancing on our spacecraft.
We didn't look at that until pretty good either. You got time.
There was the charts were supposed to show that with all the perturbations that we are within bounds, within safe bounds for the design. We don't exceed the impact trajectory angles, and it's all within safe design for the probe. There is still some margin on that.
What is the allowable entry angle for that?
We target a nominal minus 40 degrees gamma, and there is a plus or 5.
You're talking about flight path angle?
Yes.
I'm asking about angle attack.
Okay, alpha, and so I was getting there. We target a nominal 0 alpha, and there is also a 5-degree window on that.
So you're allowed 3 sigma, 5 degrees.
And that was.
And what can you achieve?
We achieve everything of ours fits within 1 degree. Through all the perturbations, our flight or our angle of attack is controlled to within 1 degree, and we have a design for 5-degree margin.
Good for you.
Okay.
Just to clarify that Mach number, how well do we know this being sound under this?
Again, the person to answer that question is not here at the moment. But I'll be happy to direct it to you when it shows up, and you can answer that much better than I can. Okay, so now I'd like to pass it off to Ed.